All right. So we're starting into chapter five, and chapter five, has this title of continuous random variables. But I would say probably the most important thing about chapter five um, is going to be this idea down here that the area underneath a curve is equal to the probability of an event occurring. So previously, when we talked about probability, like in chapter three, um, we'd calculate the probability of an event, and that was equal to the order of the event over the order of the sample space. And so this is like an algebraic equation. Okay. And that's how we calculated probability. But now, from this chapter forward, we're not going to think of probability in an algebraic sense like this. Instead, we're going to think of probability as being equal to an area. Right? So what do I mean by that? So what we've got here, which is called a probability density function, or a PDF. This probability density function is an algebraic equation that describes the probability of certain events. Okay, so here our probability density function is this equation right here. F of x equals 0.147, and it's for values of x between 2 and 8.8. So, um, so this equation between 2 and 8.8, so here's 2, and 8.8 there is just shy of 9. And you can see that this equation, f of x equals 0.147, that defines this horizontal line here. Now, technically, this horizontal line describes what's called a uniform distribution. Okay, and it's uniform because the probability of a 2 coming up is going to be 0.147. The probability of a 3 occurring is 0.147. The probability of a 4 occurring is 0.147. The probability of 5, 0.147. 6, 0.147. 7, 0.147. And 8, 0.147. How about 5.5? 0.147. So the probability of any number between 2 and 8.8 occurring is going to be 0.147, which is what this was describing here. Um, Now notice that, I was at first choosing these integers, 2, 3, 4, 5, 6, 7, 8. But then I said, well, what about the probability of 5.5? That's 0.147. What if I wanted the probability of 5.8113? Well, 5.8113 is going to be somewhere right about here. And if I go up, that's going to be 0.147 as well. So notice that I started with choosing numbers that were discrete values, countable values. And I moved to numbers that were measured, that had decimal points of accuracy, that were not countable. So we're talking about probability density functions that are continuous, that represent continuous distributions. So continuous means that we can just choose any value with any decimal accuracy between 2 and 8.8. Now, what I mentioned earlier about area being equal to probability. Now, what that means is if we take this same function and we look at this graph that I've got down here. So here we've got the probability density function, which is this horizontal line that defines our uniform distribution. What if we wanted to know the probability of x being between 3 to 7? So what's the probability of randomly choosing an x between 3 and 7? Well, that probability is going to be exactly this area that you see underneath the curve, underneath that red horizontal line, and above the horizontal axis, bounded on the left and on the right by 3 and 7. This area is equal to the probability of that event occurring. So tying probability to an area is a different concept. Okay, is a different concept than calculating probability using an equation. Now, this idea of area being equal to probability, this is not a one and done thing. It's not like we're going to learn this in chapter 5 and then you're not going to see it again. This is the predominant idea from now until the end of the course. So this is something that you want to continually think about and try and wrap your brain around. Now, the reason why I'm doing this in chapter 5 is because right now the area is something that's easier to visualize because we're talking about the area of a rectangle. And the area of a rectangle is something that a lot of people have had experience with, right? Maybe you had a picture frame, and the picture frame might have been like 18 inches wide and 12 inches tall. And so if you wanted to calculate the area of the picture frame, well, that would be the length times the width. So area of a rectangle is length times the width. And so whatever 12 times 18 is, that comes out to 216. So the area would be 18 times 12, or 216 inches squared. Okay. So maybe this is dusting off some cobwebs, but area of rectangles, is something that you would have seen in several prior math classes to this one. And so I thought that this would be the easiest introduction to this concept of area being equal to probability, and that's found here in chapter 5. So, in short, a probability density function is the function that defines the uniform distribution. Okay, so it's the function that defines the uniform distribution. And in the next chapter, in chapter 6, the probability density function won't be the function that defines a uniform distribution, but it'll be the function that defines another distribution called the normal distribution. Okay. All right, so let me go ahead and stop because this is kind of like one self-contained topic. No, I could keep going. Okay, so on this topic of area, So a cumulative distribution function is a function which defines the area under the curve of a probability density function. The area under the curve that we're talking about is going to be the area under the curve and above the x-axis. And the area under the curve will always equal 1 maximum. The probability is usually found in intervals of x, so x being between 3 and 6, for example. We won't be calculating the probability of x occurring to be equal to one particular value, because one particular value cannot have an area underneath it. And you'll kind of see that here in a minute. So in this section, we're going to be looking at uniform distributions, and we're going to be calculating the area under uniform distributions, which take the shape of a rectangle. But you could easily also calculate the area underneath an exponential distribution. So what makes this an exponential distribution is the distribution is defined by this exponential curve. Whereas on a uniform distribution, it's defined by this horizontal line or this horizontal curve. And I just mentioned that in chapter 6, you're going to be looking at a normal distribution. And a normal distribution has this bell-shaped, kind of hill-shaped symmetrical curve to it, and we'll be calculating probabilities by calculating the area under the curve and between values of x. Okay, so I think that's enough for this quick little introduction. Again, have in mind area equals probability. Okay, let me know if you have any questions.